Hello class, and welcome to our guided notes section on Skill 12 from Unit 4. So this is kind of exciting because this is our last skill for Unit 4. So after this video, you will be done learning all of the Unit 4 skills and we can begin reviewing and prepping for our test next week. But also, you should be very proud of yourselves because that means you've officially completed half of a unit in distance learning after today. So, good job. Now this last skill is all about solving. And I don't know if you've noticed, but with all of our units that we've had since the beginning of the school year, they typically end with solving the types of functions we've been studying or equations that use the types of functions we've been studying. And this Unit 4 was primarily on inverse functions. And then we started looking at radical functions as well, because they are inverses of power functions, which was in our Unit 2. So that's why we decided to group them in this unit with inverse functions. So that's what we're going to be solving equations with, is the ones that have radicals, square roots, cube roots, fourth roots, etc. Now remember, it's important to understand that there is no one set process for solving these types of equations, right? There's several different types of equations with radicals. The idea that I want to stress is I want you to think about the problem when you are solving it and the best strategy to isolate x rather than memorizing how to do it, okay? Think about how you can isolate x in each unique scenario as opposed to memorizing how to do it. Now, I have a set of general steps, guidelines that typically work most of the time, and that kind of give you the big picture. So usually we're trying to isolate the radical in order to get the variable outside of the radical, and then eventually we want to eliminate it by using the inverse operation. Once all the radicals are gone, we basically just want to solve for the variable. The idea ultimately is always to solve for the variable. And sometimes, like when we had rational equations, your answers may be extraneous, meaning they cause the equation to be undefined or not actually create a true value when you plug it into the equation. So always make sure that your solutions make the equation true. Some of them may not, okay? But let's just get to it. Let's start with our very first example. Right here, you can see here I've got the variable y is underneath the square root sign. So ultimately what I'm trying to do is solve for y. That is my goal. But before I can get to the y, I have to get it out from under the square root. So in order to solve for y, I'm going to need to isolate the radical, okay? Isolate the square root sign. So to do that, I'm going to subtract 5 from both sides to get it away from the radical, okay? And so when I do that, I've got the square root of 2y minus 1, and that is now equal to 3 because I had to subtract 5 from 8. Then I need to eliminate that square root, right? This has an index of 2. So the opposite operation or the inverse operation would be to square it. Okay, so I'm going to do that to both sides. Whatever you do to the left side, you have to do the right side to maintain equality. Since those are inverse functions, the square and the square root will cancel out. So on the left side, I will just have whatever was underneath the radical. The input basically is what I have left. And then on the right side, I square the 3 and I get 9. Now from here, you can see this is just a regular two-step linear equation, and we will just solve that like normal. So basically now I'm trying to simply isolate the y. So I added the 1 to both sides, and then I will go ahead and divide the 2 from both sides as well to fully isolate the y. 9 plus 1 is 10. Not 9, and then 10 divided by 2 is 5. So in this equation, when I solve it using our algebraic operations, I get y equals 5. So now what I want to do is check, does that make the equation, my original equation, true? So what I will do is I will plug in 5 for y, okay, in that equation to see if it makes it true. So under the radical was 2 times the y value minus 1. So now it's 2 times 5 minus 1. Outside of the square root, I added 5, and then all of that was equal to 8. So this would be 10, right? And then 10 minus 1 would be 9. So square root of 9 plus 5, we're trying to see, does that equal 8? And then as we know, the square root of 9 is 3. So yes, this checks out. So this is definitely my solution. So then I'm done. Okay, so let's move over to number 2. Number 2 starts out very similar. Okay, I've got a square root. My variable that I'm trying to solve for is underneath that square root. So ultimately I want to solve for x. But I can't do that until I get it out from under the radical. So I need to isolate and then eliminate the radical. But it's important that you isolate it first so that you can just do the inverse operation to just the radical instead of two things on the same side. So I'm going to subtract 9 from both sides. And that leaves me with the square root of x minus 1 on the left, and then 1 minus 9 is negative 8 on the right. So I want to kind of put a star right here. Something about that should be striking you as not like so good. But I'm going to keep going, and then you tell me what that something is. So the next thing I would want to do is eliminate the radical. So then I will square both sides, because this again has an index of 2. So it's a square root. So then raising it to the power of 2 would be the inverse operation. And I'll square the negative 8 on the right side. So when I square a square root, they cancel. And I'm left with just whatever was on the inside. So it's x minus 1. And then when I square negative 8, I get 64. So then I just need to solve for x by adding 1 to both sides, and I get x equals 65. Okay, so that's my answer. So now what I'm going to do is I'm going to check. Does that make the equation true? So let's find out. So I get 9 plus the square root of 65 minus 1, and then I have to see if that is equal to 1. Well, 65 minus 1 is 64. And then the square root of 64 is 8. And then that does not equal 1. So something went wrong. Something went wrong somewhere, and that something was right here. So if you remember in skill 6, when we were talking about even roots, square roots, fourth roots, sixth roots, etc., we have to always take the principal root. And so that is kind of the issue that we are dealing with here, is a principal root must always be positive. When you're dealing with even indexes and you're taking square roots, even roots of something, it must always equal a positive. It's not supposed to equal a negative. Right here was where things went wrong. And so that's why later on, when I went to plug it back in, I get positive 8 right here, right? Because I'm taking the square root of 64, which is the principal root, which is positive 8, and 9 plus 8 does not equal 1. Now, if I was allowed to take negative roots, this could work, because I could say, oh, the square root of 64 is also negative 8, right? And 9 minus 8 does equal 1. But that's not what we're supposed to do. We're only supposed to take principal roots. And so therefore, this problem has no solution, especially not given our requirements of making sure that all even roots have principal roots, positive roots. So when that happens, when you get a situation like this where you plug a number into the equation and the result is not a true statement, that number is not a solution, and you need to answer by saying no solution instead of by saying, whatever the number is. And that basically you can tell that this will be the answer right at this step. Once you have an even root equal to a negative, you can just stop right there and say, oh, that's not going to have a solution, because even roots can never equal a negative. Moving on to number 3, we again have a variable m. That's underneath a fourth root now. Now we're looking at higher roots. And the goal is the same, is to eventually isolate m. But before I can do that, I need to isolate the fourth root. So I'll begin by just moving away the 1. I'll add it over here to the 14. So then I have 5 times the fourth root of 2m plus 1, and then that equals 15. But I want to also divide both sides by the 5 before I get rid of the radical. I want to completely isolate the radical before I eliminate the radical, because that makes it so much easier and less prone to error if I can isolate it first. So the 5 is being attached to the 4th root through multiplication, so that's why I remove it through division. And so then when I do that, I'm left with just the 4th root on the left side, which is what I wanted, and then 15 divided by 5, which is 3 on the right side. Okay, now I got to the place where I wanted, where the radical is completely isolated. Now it is a 4th root, so to cancel it out, I'm going to need to raise it to the 4th power. And then to keep the equation true, I'll need to raise the other side to the 4th power as well. So the power you raise the radical to must match the index. That's how they will cancel each other out. And then I'll be left with just the 2m plus 1 that was on the inside. And then on the right side, I'll have to go ahead and multiply 3 to itself 4 times and get 81. Okay, and then from here, it's just a regular one-step equation, very similar to the end of problem number 1, just a 2-step linear equation. So I will just isolate m. I subtract 1 from both sides, and then divide both sides by 2. And then I get m is equal to 40. And I'm pretty sure I'm right, but let's just check, right? It's not like we got anywhere to be right now, so we have time to go ahead and check our answers and make sure that they're right by taking that 40 and plugging it back into m from the original equation. So the original equation had 5 times the 4th root of 2 times m, whatever that is. In this case, I'm saying it's 40, plus 1, that was under the 4th root. And then I'm supposed to subtract 1 from the 4th root, and then that's supposed to equal 14 if I did this right. So let's find out. So 5 times the 4th root of 2 times 40 would be 80, plus 1 minus 1 equals 14. Of course, 80 plus 1 is 81. So 5 times the 4th root of 81 minus 1 equals 14. We're not sure. We're checking. 4th root of 81 is 3, because 3 times 3 times 3 times 3 is 81. So then this 4th root turns into a 3. So 5 times 3 minus 1, yes, that does equal 14. So that tells me that m equals 40 is a true solution. So example 4 will be similar because it's just set up in a similar way. It is an odd root, okay, 3rd root, so we'll have to keep that in mind. So I begin, as usual, by isolating the radical so that eventually I can eliminate it. And so then I have the 3rd root of 3y plus 1 equals negative 2. So you might be like, wait, there's a negative here, Miss Lasner. You told us before that if the radical equals a negative, then there's no solution. And I will say yes, but I said that it was an even radical. Okay, if it's an even radical, those are the ones that are not allowed to be negative, but this is an odd radical, and odd radicals often will equal negatives. So not only are they allowed to, but it happens a lot. So this scenario is solvable. Okay, let's compare. Example 2, my radical was even. It was a square root. And that's the kind of radical that's not allowed to be negative. But in number 4, my radical is a cube root. It's odd, an odd index. And so it is allowed to be negative. And so this is okay. And we can still solve from here. We can and should continue to solve. Okay? So it's only even roots that have issues, which is why I like odd roots better. They're less maintenance. Okay, so let's go ahead and raise both sides to the power of 3. Also notice when I do that, the negative stays there, right? There's no confusion as to what the final value should be. And then the power of 3 will cancel out the index of 3 because they're the same number. And it'll leave me with a 3y plus 1 on the left. Meanwhile, negative 2 to the 3rd is negative 2 times negative 2 times negative 2. So 3 negatives. The first 2 negatives cancel, but I still have the 3rd one. So this ends up being positive 4 times negative 2, which is negative 8. The negative stays. So that's why odd roots are fine, because if you cube a negative, the result is negative. Therefore, you can cube root a negative and get a negative result. So we can basically just solve from here. I'm going to subtract 1 from both sides to isolate my variable y. I get negative 9, and then I will divide by 3. And I get y equals negative 3. But I'm still going to check, just because maybe I made a different kind of error somewhere else. And if I can check, I might as well. So let's see. If the third root of 3 times my answer for y plus 1 plus 2 on the outside equals 0. Let's find out. So 3 times negative 3, that part's negative 9. So this would be the cube root of negative 9 plus 1, which is negative 8. Plus 2, does that equal 0? And I can see that it will, because the cube root of negative 8 is negative 2, and negative 2 plus 2 does equal 0. So we were correct. Y equals negative 3 is the answer. We're good to go. Moving along to question 5. Things are getting a little bit trickier now because there's no radical sign in my equation, but there is this rational exponent. So we need to understand that that basically is a radical. That's a square root. And you can either rewrite it that way or just recognize it's a square root. But I have an even different situation where I have a variable outside the square root as well as one inside the square root. So this is just going to be a harder problem because when I square both sides, I'm going to have to FOIL this side. So what I'm about to do serves no math purpose, just more of a, I don't know, it's just a way to avoid making mistakes. I'm going to subtract the 2 to the other side so that I don't have to FOIL these. I do not want to have to FOIL x plus 3 to the 1/2 plus 2. Like, that's not something I want to do. So I'm subtracting the 2 to the other side so that when I square both sides eventually, I will only have to FOIL the right side. And it's a lot easier to FOIL a binomial like this instead of something to a 1/2 power. And it's negative 3 because I had to add, right? Negative 1 minus 2, you actually add up all the negatives. And then the x is still there, so there's x minus 3. Okay, so this 1/2 power, as I mentioned before, means a square root. It means the index is 2. So you can rewrite it that way if you are more comfortable. So maybe I will right now, because then it will look more like our original questions. And then if you want to cancel a square root, then you need to square both sides. Okay, so the square root and the square will cancel on the left side, and you're just left with x plus 3. But on the right side, you have subtraction. And in our notes from skills 10 and 11, we reviewed that you cannot distribute an exponent over subtraction. You instead need to FOIL. Okay, so you're going to have to write it out twice, right? X minus 3 squared would equal x minus 3 times x minus 3, and then you'll need to go ahead and FOIL that. So x times x times negative 3 times x, negative 3 times negative 3. So on the left side, I have x plus 3. On the right side, I have x squared minus 3x plus 9. And then I can combine those middle terms. Now, I don't know if you guys are noticing something. I hope you're noticing something because it's been a goal of mine all year to make this pop out at you. But my equation now has an x squared. So that means we are now dealing with a quadratic. This is not a linear equation. This is a quadratic equation. This is a game changer. This is where you need to get one side equal to 0, right? We don't do that with linear equations. We just isolate the variable. But once you have a situation where the variable is squared at some point, you have to change your game plan, okay? Instead of trying to isolate x, you get one side equal to 0 so that we can either factor the equation or use the quadratic formula, one or the other. But in both of those scenarios, you need a 0 on one side. So I'm going to subtract x from the left. I'm going to subtract 3 from the left, and I will combine those with their like terms on the right side, and both of those will cancel to be 0. So now on my left side, I have 0. On my right side, I have x squared minus 7x, because those add together, plus 6, because 9 minus 3 is 6. And this looks factorable because I know that the numbers -1 and -6 will add up to -7. So really quick, I was basically sort of doing this in my head. Two numbers that multiply to 6 but add to -7, well, they'd have to both be negative, and it would have to be 6 and 1 for them to multiply to 6. And they'd have to both be negative to add to -7. So then, since these are equal to 0, you just take each separate one and set it equal to 0 and then solve for x. So for this one, I get x equals 1. And for this one, I get x equals 6. Okay, but especially when you have two answers, you should check both, because one of them might work and one of them might not, or maybe they both won't work, or maybe they both will work, but you're going to need to check at any rate. So let me go back to the beginning here, and we're going to check our answers. So the first one I'm going to check is x equals 1. We're going to check x equals 1 in the original equation. So wherever there's an x, I'm just going to replace it with a 1 and see if it works. So on the right side of this equation, I get 0. And then on the left side, I get 4 to the 1/2 plus 2. Well, 4 to the 1/2, that's one of the two factors that multiply to equal 4. Or you can think of that as the square root of 4. So that's just 2. But 2 plus 2 is not equal to 0. Okay, so right away I can see that my solution that said x was equal to 1 is actually not a solution. Okay, so now I'm going to check the second one. So I'm going to check the one that said x was equal to 6 with my very original equation up here. So I'll say 6 plus 3 to the 1/2 plus 2 is equal to 6 minus 1. So on the right side I have 5. And then on the left side I have 6 plus 3, which is 9 to the 1/2 plus 2. So 9 to the 1/2 means one of the two factors that multiply to equal 9, or the square root of 9, which is 3. And 3 plus 2 does equal 5. So it looks like my one and only solution, even though I ended up with 2 of these when I solved, only one of them actually makes the equation true. And so I only have one answer, x equals 6. So always check your answers, because sometimes they come out to be extraneous solutions. Moving on to number 6. This one is also challenging because I have two separate radicals that are separated by subtraction, which means, if you square both sides, you would have to FOIL this side. And I do not know about you, but I do not want to FOIL that. So again, what I'm about to do is not really for a math reason. It's more because I don't want to FOIL that reason. So I'm going to add the square root of x plus 35 to the other side. I would rather FOIL that with a number rather than another radical. So I'm just doing that to make my life a little bit easier. So on the left side, I just have a single radical. And then on the right side, I have this binomial that I will have to FOIL. So I will get right to it. So I do need to square both sides to get rid of this square root. But you'll see it doesn't completely isolate the square root on the other side, but we'll just take it one step at a time. On the left side, the square and the square root will cancel because it's just one single expression, and it will just leave me with x plus 8. On the right side, I will need to FOIL. So I need to write this out twice and FOIL. Okay, so on the left side, I still have x plus 8. Now on the right side, I have -3 times -3, which is 9. And then I have -3 times the square root of x plus 35, which is just -3 times the square root of x plus 35. The outside number has to stay outside and the inside stuff has to stay inside. And then I have that same expression again, -3 times the square root of x plus 35. And then I now have to multiply the two square roots together. But I'm going to write it this way. If I multiply x plus 35 to itself, I get x plus 35 squared. If I get x plus 35 squared underneath the square root, they will cancel each other out, right? that square will undo the square root. So that radical goes away. So that's nice. And then since these are similar index and matching radicands, I can go ahead and combine these. These are like terms and they're both negative. So I actually would add up all that negative. So it's going to be, the 9 is still there, but then these two middle terms become -6 square root x plus 35 because I added up the two -3's that were in front of the matching square roots. They had the same index and the same radicand, so they can be combined. Meanwhile, this square root goes away, so I just get x plus 35. Okay, so now I have a very complicated looking equation, but let's see if we can start combining like terms. I can combine the 9 with the 35 and get 44. And I think that's about it. But what I can do now is completely isolate the remaining radical. What I mean by that is I can move all this other stuff away from it. So I will do that. I'm going to subtract the 44 to both sides, but specifically with 8, since that's the like term. I'll subtract x from both sides. Now this is nice. Notice this. Whew, these x's cancel out. That's going to make our life a lot easier. Okay, so then when I do 8 minus 44, I get -36, and that's equal to -6 times the square root of x plus 35. And at first I was thinking, uh-oh, I've got an even root, right? This is a square root, which is even. That was equal to a negative, so maybe there's no solution. But then I also see this other negative right here. I still actually need to divide both sides by -6 anyway to isolate the radical, so then the negatives remove themselves as well. So that was like another nice thing that happened. Okay, so now I just have this. Now that is actually not bad. That is not bad at all. It was so crazy at first, but just taking a deep breath and walking through the steps one at a time, things sort of worked themselves out and canceled themselves out to create a decent radical equation. I just need to now square both sides to get rid of the remaining radical. It will cancel out, and I get 36 on the left, and then just the x plus 35 on the right. And then I just solve for x by subtracting 35, and I get x equals 1. So that is my answer for number 6, but let's go ahead and check, right? Just to make sure, we're going to just check with the original equation that's written at the very beginning. So I'll just plug in 1 for each x. So it was the square root of 1 plus 8 minus the square root of 1 plus 35 equals -3. So that's the square root of 9 minus the square root of 36 equals -3. And yes, that will be true, because 3 minus 6 does equal -3. So this is our answer for number 6. So now we come to our last two examples, number 7 and 8. I just wanted to show you one problem where the exponent was not just a simple root. It has a power and a root. It's a 2/3 power. So I'm going to show you two different ways to do this problem. I'll show you the longer way first that might make more sense, and then I'll show you kind of a shortcut for those who are ready for it. So when you have a rational exponent with a numerator that's not equal to 1, we have to remember that that is the power, and then the denominator is the index. So I'm going to write this as the cube root of x plus 5 squared. So that's really what that is. It's the cube root of x plus 5 squared. So I now need to undo both a power and a root. So maybe I'll undo the cube root first by raising both sides to the 3rd power. That'll undo a cube root. But what I'm left with on the left side is a perfect square, x plus 5 squared. And then 4 times 4 times 4 is 64. So I have 64 on the right side. Okay, so I've got x plus 5 to the power of 2. So the way you undo a power is you take the root. So so now I need to square root the 64. I need the same index to match the power so that it will cancel out. And then I get x plus 5. But here we have to be careful because the x plus 5 was being squared, which is why I had it equal to a positive. But when you square root it, excuse me, it could be positive or negative 8. So this actually has two possible answers, which we'll have to solve both scenarios. The one where it's positive 8 and then the one where it's negative 8. Okay, so here I get x minus 5 is 3. That's one possible answer. And then here I subtract 5 from both sides and I get negative 8 minus 5. So you actually add them together, would be negative 13. So two possible answers. Let's check to see which ones work. So I'll check the 3 first. So I get 3 plus 5 to the 2/3, and we're checking, does that equal 4? So that's 8 to the 2/3. And then we remember the fact that 3 is the index, so this is a cube root of 8, and then 2 is the power, so I need to square that. Question is, does that equal 4? So the cube root of 8 is 2, and 2 squared equals 4. So yes, so 3 worked. The one that was equal to positive 8 worked. Okay. Now we're going to check x equals negative 13. So then I get negative 13 plus 5 to the 2/3 is equal to 4, question mark. So negative 13 plus 5 is negative 8 to the 2/3 equals 4. We're trying to find out. So then I do the same thing, cube root of negative 8, and square that. So the cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 equals negative 8. And then if I square that, yes, that does equal 4. So both of these solutions worked, positive 3 and negative 13. So remember, when you're going the other way, when the variable that you're solving for is being squared and you are square rooting it and trying to get to the source, then we have to remember, well, the source could have been positive or negative, right? It's only the outcome of a radical that has to be positive, but the inside of a radical could be positive or negative, especially if that inside is being raised to an even power. So it turns out both solutions worked, so we need to find them both. Okay, the other way to solve this problem, this is option 2, is to leave it as a rational exponent and use the reciprocal exponent to cancel it out. So I could raise both sides to the 3/2 power. Raise both sides to the 3/2 power, because when you raise a power to a power, you actually multiply those powers together. So you get x plus 5 to the power of 2/3 times 3/2. But 2/3 times 3/2 equals 1, because everything cancels. So then that means there is no more power on the left side. You're just left with x plus 5. And then 4 to the 3/2 gives us the square root of 4 cubed. So then I get x plus 5 equals the square root of 4, which is 2 cubed, and then that equals 8. So I get x plus 5 equals 8, and then I can subtract to get 3. Well, it didn't actually find both of our solutions, so that's interesting. It only found one of the solutions, so you would kind of have to go about it this way to get both. But it is one option for finding one of the solutions. So last but not least, number 8, I wanted to show you because it's actually not a radical equation, but it can trick students into thinking that it is. So I've seen questions like this appear on like the SAT or the GRE. They, those type of tests, competency tests or placement tests, just to see if you can notice the difference here. And notice that the x is actually not underneath the square root. It's outside the square root, and both of them are just to the first power. So this is actually a linear equation. I'm not going to need to square both sides. That's not something I have to do. All I need to do is isolate x. So don't let that GRE fool you. Don't let that SAT fool you. If the x is not under a square root sign, just isolate it. So what I'm going to do first is combine the 3 with the 5. So I'll add 3 to both sides. And then I get x times the square root of 5 on the left equals x plus 8 now on the right. Now what I need to do is combine my x terms, but I can't really add them because one has a radical and one doesn't. So this is what I do instead. I just write it as x rad 5 minus 1x, only to make it helpful for my next step. And then I go, okay, they each have a common factor of x. I'm going to factor that common factor of x out. So that's why I wrote the 1 there, because then it makes it more obvious when I factor an x out, I'm left with a 1. So I have what we call it's an irrational number that is in simplest form. I can't really combine it, but it has an irrational part and a rational part being added together or subtracted. So it's kind of like a binomial radical expression. So they have to stay connected like that. So when I go to divide both sides, because I just want to get x alone. So now I need to go ahead and divide both sides. I have to make sure to keep the whole binomial together when I divide it. So then on the left, I now have x isolated. And then on the right, this is my answer. Now, for me, I'm happy if you just get this far. Okay, I'm like, that's awesome. Woo, good job. But I know a lot of times, especially if the question is multiple choice, they're going to want you to simplify all the way and rationalize the denominator. It's that thing where you have to multiply the numerator and denominator by what we call the conjugate. This is just a review of rationalizing the denominator. And that is just to eliminate all the radicals that are in the denominator. So then in the numerator, I get 8 times the square root of 5 plus 8. And then all over the square root of 5 times the square root of 5, which is 5. And then plus the square root of 5 minus the square root of 5, which will cancel the radicals. And then lastly, negative 1 times 1, which is negative 1. So then that ends up equaling 8 rad 5 plus 8 all over 4. And then that can be simplified even further because of the common factor of 8 in the numerator. So I factor that out. And then I recognize the common factors between the denominator 4 and the numerator 8. I can divide a 2 out of both of those. No, actually I can divide a 4 out of both of those, leaving a 1 in the denominator and a 2 in the numerator. Final answer would be 2 times the square root of rad 5 plus 1. So I'm okay with this answer right here. This is sufficient for Mrs. Lasner's test or quiz. But those of you that do plan on taking SAT or GRE or any kind of placement exam at any point in the future, you will need to know that these are equivalent expressions. And if you're taking a multiple choice test, they may not put this as an answer choice. They may only put that. And so you need to know how to convert from this form to that form. And that's where multiplying by the conjugate comes in. We call it rationalizing the denominator. And that concludes our video notes on Skill 12. Congratulations finishing Unit 4. And if you need any help with the practice, let me know.